The conversation about plastics and sustainability is one that's become common in our daily lives. With climate change awareness being talked about on the news, on social media, and even in school science lessons, we, as consumers, are finally realizing the impact that we can have on the planet. While many of us try our best to use reusable bottles and metal straws, at the end of the day, companies who perpetuate most environmental problems are the ones who need to implement changes on a wider level. With that said, in this video, we're going to be looking at 3 common polymers used in takeaway, an industry that uses a concerningly large amount of single-use plastic. But be warned, watching this video might make you reconsider getting that takeaway on the weekend. The takeaway industry is growing rapidly. Between 2009 and 2016, UK household spending on takeaway increased by 33%, which is equivalent to £2.5 billion. This trend is only forecasted to continue, especially with the COVID-19 pandemic creating increased demand for takeaways. Because of this, it's really important to consider the materials used in takeaway and their impact on the environment. But first, what exactly are polymers? A polymer is a chain of monomers, which comes from the ancient Greek, mono meaning single and mer meaning part. Polymers, therefore, come from the ancient Greek meaning many parts. To name polymers, you just take the name of the monomer and add poly to it. For example, styrene becomes polystyrene. Polymers can be primarily synthesized via 2 methods, chain growth and step growth polymerization. In a chain growth polymerization, monomers are added one by one at the end of a growing chain. The chain can only grow in one direction. In a step growth polymerization, all monomers and growing chains can react together to form new chains, and the chain can grow in both directions. The first polymer we're going to look at is polypropylene, sometimes known as polypropylene. It's very versatile and one of the most common plastics, used in takeaway boxes, disposable cutlery, plastic furniture, children's toys, and more. It's derived from propene, which is a byproduct of the petroleum industry. Despite being so widespread, 90% of polypropylene containers in the UK are sent to landfill. We'll talk more about recycling a little bit later though. Polypropylene belongs to a group of polymers called thermoplastics. There are 2 main categories of polymer: thermoplastics, also known simply as plastics, and thermosetting polymers. However, these aren't used in takeaway and we will only be focusing on thermoplastics in this video. These plastics can be heated repeatedly above their glass transition temperature and reshaped, and will harden in that form on cooling. Tupperware and other microwave-safe food containers are mainly made from a type of polypropylene called isotactic polypropylene, since its high melting point stops it from deforming. The melting point of a polymer depends on a property called tacticity. Tacticity is a description of a polymer's stereochemistry. There are 3 types of tacticity. Isotactic means that all the functional groups are on the same side of the polymer backbone. Syndiotactic means that the functional groups alternate regularly on both sides of the polymer chain, and atactic means that the orientation of functional groups is random. The tacticity of a polymer affects its physical properties, for example, the glass transition temperature and elasticity. The atactic form of polypropylene is not particularly commercially useful because it's very soft and rubbery. Isotactic polypropylene, however, due to the regularity of the polymers, can pack together in a much more crystalline way, making it harder and raising its melting temperature. In order to synthesize isotactic polypropylene, a special catalyst called a Ziegler-Natta catalyst is used. The mechanism for Ziegler-Natta catalysis is chain growth. The catalyst is usually a combination of multiple compounds. A common one is formed from titanium trichloride combined with aluminium diethyl chloride. The reactants combine to form this titanium complex, which has an empty d orbital. A molecule of propene can then donate electron density into this empty orbital, forming a new complex. The double bond opens and the atoms rearrange themselves, forming the start of our polymer chain. The titanium once again has an empty orbital. allowing another propylene molecule to react and undergo the same process. Due to the nature of the catalyst, the molecules can only react if they are orientated in a certain way, which is why this method produces isotactic polypropylene. The second polymer we're going to look at is called polystyrene. As one of the first polymers to be discovered, polystyrene has many uses in all kinds of applications. Perhaps its most well-known use is in protective packaging, in the form of foam, but as an insulator, you'll also often find it in roof and wall insulation. Its uses don't stop there. In its regular form, polystyrene is a hard, solid plastic used in kids' toys, electronic appliances, CD cases, and more. But in this video, we're talking about its uses in takeaway. This recognizable clamshell takeaway box is made from expanded polystyrene foam, which is often incorrectly referred to as styrofoam, which is actually a brand. The foam is 95 to 98% air, so it's very lightweight, which means the actual quantity of raw materials needed to manufacture it is quite low. Polystyrene, like polypropylene, is synthesized by a chain growth method, specifically free radical polymerisation. The initiation step involves the breakdown of a benzoyl peroxide molecule under UV light to form two reactive radicals. The radical then reacts with a molecule of styrene, the monomer that forms polystyrene, causing the double bond to break, forming a new radical. Once this first polymer radical has been formed, it can react with the second monomer unit in the propagation step, forming another reactive radical. This process will continue until a termination step occurs. This process is very fast. In 1 second, chains of thousands of monomers can be created. The polystyrene produced by this method is atactic, as it is made by a free radical polymerization, which has no control over stereochemistry. When it comes to the environment, polystyrene is far from the wonder material that its ubiquity makes it out to be. Polystyrene constitutes a serious threat to marine life. The very properties which made polystyrene foam so versatile and useful are the same properties which make it so damaging for the environment. It's inert, so it doesn't naturally decompose, at least not in any reasonable time frame. Estimates range from 500 to 1 million years for it to decompose fully under environmental conditions. Its lightweight structure means that it will float in the ocean and potentially be ingested by fish and other marine creatures. We'll talk more about environmental effects later in the video. The final polymer we're going to look at in this video is polyethylene terephthalate, better known by its acronym PET. This polymer is incredibly common. It's used extensively in clothing as the material polyester. It's also used in food packaging and takeaway containers. One of its biggest uses is in bottled drinks. In 2016, 485 billion PET bottles were produced worldwide. It's one of the most recycled polymers in the world, but we'll talk more about its disposal later. PET is a polyester, which means it's a step growth polymer. Both ends of the monomer are reactive. But what is the monomer for PET? There are two mechanisms to synthesize this polymer. Each one uses different reactants. Although some step growth polymers can be synthesized from a single monomer, PET is actually synthesized from two different alternating compounds. The first mechanism is a Fischer esterification. In this reaction, a diol and a dicarboxylic acid react together to form ester linkages between molecules, producing PET. This is a condensation reaction, so water is lost during this process. The second mechanism to synthesize PET is a transesterification reaction. On the screen right now is the overall reaction, which occurs under acidic conditions. We start with a diol and a diester. In this mechanism, we replace the ester group with a different ester. Firstly, our reactant reacts with a hydronium ion. Electrons in the double bond between carbon and oxygen are donated to the electron-deficient oxygen atom. The positive carbon atom is now attacked by a nucleophile. This is the diol, our other reactant. The electrons in the OH bond then move back to the oxygen atom to neutralize the molecule. The compound then reacts with another hydronium ion, using the lone pair of electrons on the oxygen atom from the original ester group. The positive charge on this oxygen causes the carbon-oxygen bond to break. As we once again have a positive carbon, a lone pair on the oxygen is donated into the carbon-oxygen bond, and our hydrogen atom is eliminated, leaving us with our product. This process happens at both ends of the molecule, forming a long polyester chain. We've already briefly mentioned ways that these polymers have a negative impact on the environment. Now, we're going to look more in depth at the sustainability of these polymers and what alternatives there are. There are many aspects of sustainability, but in this video, we're going to focus on recycling and biodegradability. Although the two terms are often used in similar contexts, the meanings are very different. A biodegradable plastic can be broken down by bacteria or other living organisms. This occurs under normal environmental conditions, and the plastic is broken down into environmentally acceptable products, such as water and carbon dioxide, as well as biomass, which is organic matter, such as plant or animal material. None of the three plastics we have been looking at are currently biodegradable, which brings us on to recycling, which is the processing and conversion of waste materials into new products. In the EU, only 11% of polypropylene containers are currently recycled. The rest are either incinerated, producing carbon dioxide, or sent to landfill. Polystyrene food containers are in fact recyclable, despite common belief. However, since polystyrene foam is mostly air, the actual quantity of recyclable material in the containers is very low. It's difficult to gather enough waste to make recycling these containers energetically viable, and because of this, most places, like the EU, simply don't recycle polystyrene foam, and it's therefore classed as non-recyclable. PET is one of the most easily recyclable plastics. Its low melting point means that it can be easily reshaped at low energies without breaking the polymer chains. Despite that, a study shows that in 2009, our recollection rate of PET bottles in the UK was only 32.7%, less than 1/3 of all bottles. In comparison, the recollection rate in Germany was nearly 94%. Even though our recollection numbers have improved significantly since then, we're still a long way off from Germany. What is it that we're doing wrong? In 2003, the German government introduced a plastic bottle recycling scheme. Depending on the material used, between 8 to 25 cents are added to the price of every bottled or canned drink. That money can then be redeemed by returning the bottle to any shop or to a bottle vending machine, as shown in the picture. Not only was this scheme a huge success for PET bottle recycling, it also had social benefits. Homeless people and those on the poverty line could earn themselves some money by looking for bottles and helping the environment. There are even some cases of people leaving their bottles and cans in front of these machines for the less fortunate to earn some money. Although this scheme seems like a no-brainer for countries around the world to implement, it still has some issues. For example, a big part of sustainability is simply consuming less. Under this scheme, the overall percentage of reusable bottles in Germany has actually sunk. As a society, surely we should be moving away from single-use bottles altogether? As we can see, the problem is more complex than it first appears. Another recent development is the banning of polystyrene foam food containers. Costa Rica has become the most recent country to ban polystyrene food containers. It joins a growing list of countries such as Guyana, China, and India. In the US, these containers have also been banned in multiple states and cities, such as Maine, Chicago, and San Francisco, which is clearly an important step forward for environmental change. But again, it's still not that simple. We have to consider the materials we can use to replace such a ubiquitous material as polystyrene foam. Other companies have already made the switch. For example, the old styrofoam burger containers used by McDonald's were phased out by 1990, using paper as a substitute. However, it wasn't until 2018 that they finally promised to remove all polystyrene from their global markets. So what other alternatives are there? There are two categories of sustainable alternatives: polymer materials and non-polymer materials. In order to be sustainable, polymers not only have to be biodegradable, but they also have to come from renewable sources. One material which fits into both categories is polylactic acid. Lactic acid itself comes from the fermentation of plant sources, such as corn. As a polyester, lactic acid can be polymerized via condensation reactions. However, the most common polymerization method is the ring-opening polymerization of lactide molecules. Polylactic acid is biodegradable. It breaks down into carbon dioxide and water. It is already being used in food packaging. Another natural polymer is bagasse, which is primarily a combination of cellulose and hemicellulose. It is a byproduct of sugar production, meaning it is renewable as it comes from plant materials. Obviously, it's also biodegradable, producing carbon dioxide and water once it breaks down. The second class of alternatives are non-polymer materials. The main type of non-polymer material used in takeaway packaging is aluminium. In the EU, around 54% of these containers are currently recycled. The issue with aluminium is not its end-of-life impact, but rather its production. Extraction and processing of aluminium require very high amounts of energy, and because of this, its overall environmental impact is actually higher than both polypropylene and polystyrene containers. In addition, the paper lid is actually coated with polyethylene, which makes it very difficult to recycle. Clearly, the way we are producing and using polymers in takeaways at the moment is not sustainable. There are alternatives out there, but both the technology and the incentives need to be developed further before we see a real change.